In this video, we're going to look at some of the loading options in Karamba. To continue with our definition where we left off, we're going to go ahead and just add in the different kinds of loads. And there are three ways that you can add a load to a model. You can use point loads, distributed line loads, and mesh loads. And really just the way that Karamba's internal logic is, all of the loads end up being distributed to a point, but there are some advantages to each type. So the most basic, if you start typing in load, you'll see these different kinds of loads. We have a point load, we have a line load, and we have a mesh load. So the point loads, what you do, well, for all of the loads, you're going to set a couple things. One is the vector, which is the direction that the load is acting in. And you can do that, the way that I typically do this is by setting a unit vector in the direction that I want it to be acting. So if it was a lateral load, I would add an X or a Y vector. And for a gravity load, I would add a Z vector. So double click and start typing unit, or just type the letter Z, and I can grab a unit Z vector, and I can plug that in. And then you can either hook a panel onto the end of this or a slider, and set your value. In this case, I'm just going to do -1. So I've got my -1, hook that into my unit Z so it's acting down. And then this has two more parameters. So I don't know what that abbreviation is for actually, but the index of coordinates is the places that the loads would be acting. And so you can do that again by setting points, or you can do it by the names of the points. And the easier way in this case, I think, is actually to use the names of the points. So if we turn on node tags and turn off element ID tags, just so we're not confused, I'm going to go ahead and plug this in so it'll show up as I'm going. And I make a panel. Then I can, right now we'll just say that all of our load is acting at point 2. So we'll go ahead and plug that in. And you'll notice we have a load arrow which is displayed here at point 2. And if I wanted to have this same load at more points, I could list those. So let's say I wanted it at 1, and 6, and 5. Okay, so I got a red error here, something happened. What happened is the way that this data is being entered in here just doesn't work for Grasshopper. So if I double click in here, and then I come over to, I believe this one is for multi-line data, yeah. So I want this to be multi-line data, click on that and click OK. Alternatively, I can right click on the panel and say multi-line data, and that just changes the way that Grasshopper understands it. And it divides the points up into separate indices. And that's what we want. So now you'll see I have loads acting at all of these points. Alternatively, I could have loads that are acting along beams, a distributed load. So I'm just going to use the same unit vector right now, and I'm going to plug this in to the vector on the line load element. And then I'm going to go ahead and grab some beam IDs. So I'm going to turn off the node tag, turn on the element tag so I can see, and I'm going to have these act on 8 and 9. So if I make a panel, well, I'm going to say 8, 9, okay. I'm going to plug that in, and once again I need this to be multi-line data, and then I'm going to plug in this load here. And now you'll see I have a distributed load. So my load is acting in a different way here, where before, as a point, it was acting in only one place. It was also a smaller load overall value. So if I put a panel on the end of this, I can show you what I'm talking about. So this is a point load, so each load is a value of -1. So in total, when I had 4 of these, my total value was -4. The distributed load, on the other hand, is a load per linear unit. In this case, my units are set to feet because I need that for another class. Yours should be set to meters. But so this is kips per foot. So this load is, -1 kip per foot across the whole length of this beam. So this load is acting, so this is a much greater load. There are another set of things to go ahead and look at with this. The orientation of what this is the orientation of the load vector, and it can be local to the element or global projection. And I'm actually not familiar with the global projection does, but typically I want to keep this global to the world, because that's the way that I'm thinking about it. In this case, that is the same. Had I drawn this line in a different way, that load might have been acting from a different direction. So if your loads are coming in a way that you didn't expect, it's good to check the orientation. Okay, so the last loading condition is a mesh load. And the way that I like to do this is actually not to create a mesh in Rhino, only because meshes are not editable in a way that I find easy, but to make a surface in Rhino, and in this case I'm just going to make this be the same size as my geometry. Go ahead and grab that surface. I'm going to add the surface component. I'm going to say set one surface, and then I'm going to mesh that surface. And in this case, I want, yes, this one, the mesh surface. So I'll plug my surface in, and then this mesh has counts in the U and V direction, which is basically the same as the X and Y direction. And this is actually going to be pretty important for us in using our mesh loading. So I'm going to set this unit vector. I'm going to go ahead and set the mesh, and then I'm going to plug this in to the load in the assemble component. Okay, so here's a great example of this reading in a funny way. So my loads are not going down even though I have a Z vector, and that's because this is local to the mesh, and the way that the mesh is oriented, Z is not the same as world Z. So I'm going to change that to global. There we go, and you'll notice my loads now are pointing vertically, which was what I want. And now, so the way that this mesh load works is that it's a distributed load. So I think that mesh loads are really valuable in general because of, if you were dealing with building a building and having a floor, you would have a load that was distributed over the entirety of that floor. And if you then wanted to figure out how it was falling on different beams, the mesh load simulates that really nicely. You don't have to continually sort of calculate. It's automatically doing tributary areas, which is great. And this is where the setup of your divisions in your mesh matters. So if I'm going to go ahead and plug a slider into this and show you. So we'll say 0 to 5 to 10. And I'm just going to go ahead and do that in both the U and V direction for now. So if I bring this down all the way to 1, you'll notice that my loads have stopped falling on all of my elements. And as I change this, it changes which elements are getting loads and which way they're getting loads. And so where your U and V count matters, so basically what's happening is your mesh is divided up into a grid. And that grid needs to have enough grid spaces such that it can divide the tributary area to your beams in a way that's useful. So if you're using a mesh load and it's just not falling on all of your beams and something seems funny, it's good to go ahead and bring your count up, and it might actually even need to be higher than 10 to get accurate enough data. So you'll notice how this is changing as this is going through. So the greater your mesh is divided, the more accurate your data will be. So that's a good thing to know.